Hello. So, what was I saying? Sorry, I didn't check the time. What was I saying? Can you see the shared screen?
Yeah.
What was I saying? I can use this formula list and the formula for tangent A plus B here. Oh, there's plus minus here, plus minus will follow. Then this bottom one minus plus means you must change the sign. So basically, tangent A plus B, if I use the formula list, it becomes tangent theta plus tangent pi over 3, all divided by 1 minus tangent theta times tangent pi over 3. Pi over 3 is how many degrees? 60 degrees. So what's tangent of 60 degrees? I think it's square root 3, right? Yes? Yes, square root 3. Oh, how do you... Okay, I think you know how to do this. I'm not gonna elaborate more. So anyways, this left-hand side equals to this. Oops. Then what do you do next? What you do next is you try to simplify. Tangent theta, we know it can be approximated as theta, right? That means that you just get approximately theta plus root 3 over 1 minus root 3 theta. That's your answer. That's it. Quadratic expression. Let me see. Why did they request for quadratic? That doesn't make sense. I missed out something. No, I think this is sorry, this is an error. It shouldn't have quadratic. It's just an expression. Can? Okay. It's a mistake with the question. Sorry. Shouldn't say quadratic. That's for part A. Okay. Mic test.
Yep.
Okay, move on to part B now. Let's go. So part B, you have sine 3 theta over 1 plus cosine 2 theta. So the problem here is that there's a 3 theta and a 2 theta. You usually cannot assume that the 3 times of angle can be approximated. Usually, actually, it depends on the question. But usually, sorry, to keep things simple, right? Usually it can be approximated. So sine 3 theta, you can approximate it with just 3 theta. And cosine 2 theta, you can approximate it with 1 minus theta square over 2, but replacing the theta with 3 theta and the brackets. This simplifies into 9 theta square over 2. 3 square theta square. Okay, now we're going to assume that we can do that. The theta is very, very small. So times 2 times 3 to it is still quite small. That means we can approximate it with 3 theta on top, 1 plus, bracket 1 minus 9 theta square over 2 below. Okay, then simplifying, I end up with 1 plus 1 is 2, minus 9 theta square over 2. You can multiply 2 over 2, then you end up with 6 theta on top. 2 times 2 is 4, minus 9 theta squared, because the 2 cancels away. Is that okay? Yeah. Oh, right. I just remember. No, there's nothing wrong with the question. I remember wrongly. Sorry. This question is not that simple. I have to get back the quadratic. They want quadratic, right? What they mean here is that you have to use binomial expansion. Here, theta plus root 3 is linear. We'll leave it on the from the numerator. We'll leave it. But this 1 minus root 3 theta, right? Very special. There's an invisible positive power 1 here. You can bring it up, which means that you actually end up with 1 minus root 3 theta to the power of negative 1, right? Can? Okay, So sorry, I have to go back to part A. Incomplete. I need a quadratic expression. What they mean is this 1 minus root 3 power theta, 1 minus root 3 theta power -1. We actually need to use the MM26. In particular, this formula here, 1 plus x power n. Okay, let's take a screenshot. 1 plus x power n. What you must have a 1 there and you must have a plus sign. And the domain will be modulus x less than 1. I'll just copy this down, then we'll use the formula. Part B, I'll have to deal with it later as well. Theta plus root 3, leave it alone. Okay, this is invisible, positive power 1. You don't do anything to it. But this guy, you can rewrite it as, 1 plus negative root 3 in front times a theta, square bracket, power -1. Can you see the pattern? 1 plus x, square bracket, power -1. Where 1 is just 1, but the x is replaced with minus root 3 theta. Can you see that? Yes, no, yes, no. You compare with the formula list. You're just doing a substitution, right? Then what happens next is you can expand it, right? The n replaced with -1. Let's see what happens. So what we have is 1 plus nx, right? N in this case is what value? Can you tell me? Power n.
General.
Sorry? What's my power n?
N.
N. It's not n, it's -1. Do you see that? Okay, so n times x means -1 times x. Okay. Then plus the next one. What would it be? N times n minus 1 over 2 factorial. That's actually -1 times n minus 1, which is -1 minus 1, which is -2 over 2 factorial times x power 2. You've never seen this before. Something new. I haven't explained it. This is called the negative factor. This is called the general version of the n choose r factorial. N choose r function. When you have negative powers. I mean, actually, I explained this before, but I didn't show you for a concrete example. With n being a negative power. You cannot type this in the calculator, okay? You cannot type in -1 choose 2. No such thing. You can only use the formula here. Okay? Okay, continue. Okay, so what we need, we need a quadratic expression. So do we need to continue expanding this to power 3? Don't need, right? Do we need this? If we are just for demonstration, the next one will be -1 times -2 times -3 over 3 factorial times x power 3. Do we need this? No, we don't need, because the question only talk about up to x power 2, a quadratic expression. If you're gonna get a quadratic, you don't need x cubed, because x cubed multiplied by anything, it will give you power 3 and higher. And I realized I made a mistake. Sorry. It's not x, right? It's not x, right? Everywhere. What should it be instead? It should be -√3 theta. The whole thing is x. Right? So that means that I should actually have -√3 theta here. -√3 theta here. -√3 theta here. Okay?
Okay.
See, x is -√3 theta. So we're gonna expand everything out and simplify first. So we end up with, let's see, theta plus √3 multiplied by 1. This is minus become a plus √3 theta. Plus this one is negative times negative gives me positive, because there's 2 copies. Even number of negatives gives me a positive power. 1 times 2 is 2 over 2 factorial. That's just 1. I can simplify. Then -√3 squared becomes just a 3 theta squared. Plus, let's just expand this for fun. Negative, negative, negative. That gives me an overall negative sign. Minus. 3 times 2 times 1 over 3 factorial. That happens to cancel away, right? 1, 2, 3, 3, 2, 1. They cancel away, that's 1. Then multiply by negative root 3 power 3. So that gives me a negative 1. Then root 3 power 3. Negative 1 power 3 gives me negative 1. All odd power is really just negative. So I'll just neatly cancel away like this. Then root 3 power 3 and theta power 3. Okay, close the bracket. And then I'll just put this square bracket here, and then I put a cross. I don't need power 3. Okay, so we simplify it down to just the power 2 terms, and then we expand out up to the quadratic. So let's see what we get. Let's see what we will obtain when we multiply this out. Approximately. And this will be equal to, let's expand out everything. So root 3 times 1 gives me root 3. Then I now want the theta terms. What can I do? I can take root 3 times root 3 theta, theta times 1. This gives me plus theta bracket 1 plus root 3 gives me 3. Does that make sense? Or maybe I show a bit more. Okay, root 3 times root 3, so root 3 squared. Following so far?
Yeah.
Yeah, go back to your binomial theorem expansion now. Plus theta squared times, I factor out the theta first. I mean, theta squared first. How do you get theta squared terms? Theta times theta, that's 1 times root 3. Plus, next one is root 3 times 3 theta squared. So that's 1 times 3. Sorry, root 3 times 3. Okay, good. Simplifying, I end up with, this is root 3 squared, which is 3 plus 1 is 4 theta. Plus this guy is 1 times root 3 plus 3 times root 3, that's 4 root 3 theta squared. Then that's your answer. So let's just confirm whether this is a good approximation of what we have, tangent theta plus 3. Tangent of theta plus pi over 3. Let's take a look. Let's take a look at the decimal screen. Okay, let me delete everything. So we start off with y equals to, because modern technology, then we can do this. But in the past, this you have to get, you can only sketch it approximately. Then for this other guy, the root 3, square root 3 plus 4, in this case x, and then plus 4 root 3. 4 square root 3 times x squared. Let's look at the graph here. What do you notice? You notice that this part is almost overlapping, right? For small values of x, very, very small values. So that just tells you that this is a good approximation of tangent x plus pi over 3. But beyond that, beyond this circle, it's definitely a very bad approximation. It's getting worse and worse. Okay? Is it clear? Like beyond 0.22, let me just change the scale, then it will look nicer. 0.22, this one is just 0. You see, it's very, very close, but then the blue curve at the small values of x, it's very, very close, right? But eventually the tangent theta just shoots upwards, and it's totally off already, the approximation. Is it okay?
Yeah.
Clear? Yeah, so we must remember how the curve looks. It's only good for small values of x. And we can calculate the exact interval of values of x where this is valid. On this interval. So let's do that. So go back, and I have to explain the interval. So the binomial expansion that we just did, right? Using that funny formula, 1 plus nx plus n times n minus 1 over 2 factorial times x squared. I'm just reading out the MF26. What formula am I referring to? That fellow here. Oh, there is one piece that I didn't screenshot over. Let me go back to the MF26. It's the right-hand side column. In particular, this part. They're telling you that modulus x must be less than 1. They're telling you small values of x, where small is defined to be this fellow here, has to be satisfied before you can use the expression. So let's see. Modulus x less than 1. Modulus x less than 1. So what is x in this case? Can you tell me what's x in this case? One plus x power n. What's my x in this case?
negative root 3.
This fella, right? And we need modulus x less than 1, but contextualize the x must replace with negative root 3 theta less than 1. And so that means that the domain, sorry, not domain, I should call it radius of convergence. That's a technical name. It's known as modulus of something less than 1. What is the something? In this case, is root 3 theta. Expand out, you can end up with modulus root 3, modulus theta, multiply between them, less than 1, which means you get modulus of theta less than 1 over root 3. Because root 3 is already positive, you can drop the modulus. You divide by positive, do you need to change inequality direction? Yes, no?
Yeah.
No, don't need. Because here is a positive value, divide by positive, you keep the same direction. No flip. No flip. Because root 3 is positive. Okay? When you divide by a positive, you don't need to flip. Only when you divide or times by negative, then you have to flip the direction of the inequality. So now this one not enough, you must expand it out, and you get negative 1 over root 3 less than theta less than 1 over root 3. What does this mean? What does this mean? It means that if I go back to my decimal screen again, you see that from x equals to, here I have to use x because of the way that decimals works. I cannot use theta. From x equals to negative 1 over root 3, the green line, to x equals to positive 1 over root 3. Okay, x equals to 1 over square root of 3. This, what do I call? How do I describe it? This blue color curve is a good approximation of the red color curve. Okay, maybe you can argue that it has to be even smaller because you see the moment you expand this part, it's definitely off already, right? It's getting way off when it's within this interval. Yeah, right. And that's all for this part. It's called the radius of convergence because of technical issues. I haven't taught you geometric series yet, so it doesn't make sense to talk about it. I'm teaching you I'm skipping the usual sequence, and I jump straight to Maclaurin series because that's what you need for engineering, like so. Okay, Maclaurin series. Okay. Good. Then part B, not enough. Part B still have us. So for part B, let me just bring down the working because I need more space. For part B, we have this guy. Same thing. We need to simplify it into a linear expression, right? So this means that the denominator we have to bring up. So 4 minus 9 theta squared, I have to bring up, and it becomes a power negative 1. Do you see the trick? Okay, positive 1 bring up become negative 1. Here you must remember that in the binomial expansion formula that we have, it only works when you have 1 plus x power n format. Keyword is a 1, keyword is a plus. 1 here, plus here. The red color highlight. 1 here and plus here. So do we have a 1 and a plus here? Don't have.
No.
So what we need to do is to do factorization. 6 theta, you factor out of 4. 4 times 1 minus 9 over 4 theta. Like this. Then power negative 1. Maybe I'll use square brackets. I'll use square brackets. Is it clear? Okay, good. So there's an issue here, which is that I only have open bracket 1 plus x power n. Here I have an extra 4 times. So what do I need to do? You need to recognize ab power m equals to, you need to remember the formula. ab bracket power m is a power m times b power n. Here the a is 4, the b is 1 minus 9 quarter theta, the m is negative 1. A is 4, b is the other fellow there, and m is negative 1. So you have to distribute the power. Basically, you end up with 6 theta multiplied by 4 power negative 1 times 1 minus 9 quarter theta power negative 1. Do we have the format yet? Almost. Yes, essentially. 6 theta over this one, 4 power negative 1 is just 4. You can simplify it further as 3 over 2 theta. Okay. I don't put the equal sign. I just simplify this now. Then multiply by this guy. You can rewrite as 1. Remember what's the two key ideas? You need a 1 followed by a plus. You have a 1 already. That's good. But do you have a plus? No. So what do you need to do? Rewrite it as plus negative 9/4 theta. I'll just change from round to square bracket. Power -1. Is it clear? Then?
Yeah.
Can so what's my x? 1 plus x power n. What's my x? What's my n? Who's the x? Who's the n?
This is your x and
Good.
your n.
Very good. Then we're gonna use the formula now. Okay. Let's copy it down so you can have a reference. So this 3/2 theta will just tag along at the front. Then you multiply by it. Now you need to expand everything. So tell me how to expand. Go.
1 plus minus 9/4 theta bracket.
Did you mean an extra negative in front? Because there's a n times the x. Can then continue.
Then plus fraction. Yeah, -1, then -2, then divide by 2 factorial, then times negative 9/4 theta.
Good. Power?
Square.
Square, x square, must remember. And then you just dot, dot, dot. Do we need higher powers? Actually, no, because in the question, I requested for as a linear expression in theta. Linear means what? You don't need power 2 onwards. So that means that we can actually just get rid of the power 2 expression. Okay? Yeah. Oh, right. I realized just now when I showed you the graph, right, of the part A1, when I showed you the graph of this √3 plus 4 theta plus 4 √3 theta square, the radius of convergence here, where we say theta in between -1/√3 to +1/√3, this is applied. This is only true when you expand out an infinite number of terms in this Maclaurin series expansion. In this binomial expansion. But here we only cut off at theta square. That's why when you see the graph, it wasn't very accurate. If you add more and more and more terms, it will actually become super, super accurate. Okay? Within the boundary from -1/√3 to +1/√3. But of course, practically speaking, it's impossible to have an infinite number of terms. It only exists in theory. So that's why you'll see the inaccuracy. Yeah. Okay. That's why it didn't wrap so nicely to the tangent curve. Exactly. Okay, so likewise over here, we are only approximating up to the power 1 term to keep things simple. That's why we will just we will not have a perfect graph that is perfectly accurate. But it's a good enough approximation. So now we simplify everything. 3/2 theta multiplied by 1 minus become a plus. Need extra time for this. Plus 9/4 theta. Okay, then this if we want the linear expression, right? You see 3/2 theta multiplied by 1 gives me 3/2 theta. Power 1. 3/2 theta multiplied by this other guy gives me some coefficient times theta gives me theta squared. But you want linear, so that means that this guy can also be gotten rid of. The answer is just 3/2 theta.
Okay.
Right, so that means 3/2 theta can approximate your answer for sine 3 theta over 1 plus cos 2 theta. Okay? Yeah. Good. Now, let's just draw a graph again. You must really see the graph because that is how this approximation idea works. Delete all. Let me just draw it again. So this is y equals to, what was the idea? It's sine 3x divided by 1 plus cosine of 2x. That's the actual graph. It looks very complicated. But the approximation is very simple. Y equals to a linear expression. What was that expression? 3/2 theta, or x in this case. You see that what happens for small values of x? The blue curve and the red curve are very close, right?
It's close.
A good approximation. Okay, that's the main idea. Of course, you can be more accurate because what we actually found was what 3 over 2x of theta multiplied by if you recall later I show you, plus 1 over 9 over 4 times x. Then you realize that, oh, actually this one also a pretty good approximation over here. But actually you realize the boundary, not as accurate. The range of valid values of x that's accurate is actually getting smaller as compared to before. Quite interesting. The worst approximation here, when you just have the original, when you just have the linear expression, actually looks more accurate. You see that? The green curve approximates the red curve a lot better. Just a straight line. Okay? Yeah. Okay. The way you could argue this is like this. Sine 3x, right, is the leading term at a numerator. So that means maybe you can approximate sine 3x with just a linear expression, right? Remember, sine theta is approximately theta. So sine 3x is maybe it's approximately 3x. Then that's why you have a y equals to 3x that looks almost the same. But you have to divide by 2 here because of the cosine 2x. Cosine 2x will be approximated with a 1 minus maybe 2x bracket square over 2. Then there's a divide by 2 there. That's why we have a 2 at the denominator. But of course, that's the heuristic way, not mathematical. If you want the exact accurate way, it's exactly what I showed you just now. Okay? Step by step. Let's do a lot of algebra. All right?
Yep.
So that is all I have for the binomial expansion. I mean Maclaurin series. I also gave you a supplementary worksheet so you can try that as homework once you're better. Or if you want more practice, the answers are also provided in that worksheet. Okay, now we move on to the integration techniques. Let me just get the notes out first. Give me a second. Save it. Oh, pause the share first. Okay, so integration techniques. Right. So I asked you to try the questions in this worksheet, right? So it is a bit difficult to cover all this in the last, I don't know, it's already 12:50. Last few minutes. But let me just show you some of them. Okay, so let's try question 1 part 4 first. Okay, in question 1 part 4, what we have is it's not moving. Very, very lousy. Okay, so question 1 part 4, what we have integral of e power sine x times cosine x, right? So the key trick here to remember is that if you have an integral of this format, let me write it nicely as f, the one. Let's say g of f of x, like this. Maybe instead of using round brackets again, I'll use square brackets. And then you're multiplied by a f prime x. This will just be equal to the integral of little g, which is capital G, of f of x, or c. Where you must understand the notation. F, you differentiate, you get f prime. Capital F, you differentiate, you get f. A bit like the SV and A, right? The displacement, velocity, and acceleration. Likewise for the G notation, differentiate, you make it smaller. Differentiate again, you get a prime. Okay, then if you work backwards, it will be integration. I. That's the notation. Can?
Okay.
Okay, so how do we use this? Okay, so basically, right, if you look at this integral, what you realize is that cosine x can be written on the left side if you really want to. Then it's multiplied by e to the power of sine x. So what you see is that this fellow here, cosine x, is f prime x. This
Yep.
sine x here is your fx.
fx.
This e power x function is your g of x. So what this means is your g of square bracket f of x is really just g of fx is what? Fx is sine x. But your g of x function is e power x, so it's e to the power of sine x. Okay, okay. Then this guy is f prime. Why? Because if sine x is fx, then the derivative will give you cosine x, which is f prime x. Right, good. So that means that you can just use the formula. Little g go upgrade to capital G. That means you integrate the g function, right? How do you integrate e power x? Oh, it's just e, okay. But then inside you don't have x, you have f of x. So you replace with sine x plus c. Done. How do you check that the integral is correct?
Differentiate it.
Differentiate it. So we differentiate e power sine x, what do you get? And plus c, differentiate the c, of course, it's just 0, so I can get rid of it. Differentiate e power sine x, you get back the same thing, but you must multiply by
Cosine
of sine x, which is cosine x. So is it correct? Is it the same as what we are integrating? Okay, so now you know. Here's a new trick. More importantly, is if you upgrade this g function to a power n. So what this means is we have the alternate version, the specific version, where we have f prime outside. I mean, it's multiplied by fx, where fx and f prime x, they are f prime x is the derivative of fx. But this time the gx function, you assign g of x to be the x power n function. Okay, so that means that you now have fx power n. Then how do you integrate x power n? In other words, you get capital G of x. It's really just x power n plus 1 divided by n plus 1, right? Correct? Add 1, get the new power, divided by new power. So here, if you use the formula from above, capital G is what? Capital G is actually just whatever power n plus 1 over whatever, over n plus 1. But here, in between the brackets is replaced with what? fx. Right? So I like square brackets outside after the round brackets, so it looks more like this. This is a new form of the formula. I think I went through this before, right? Did I not? So let's see an example. So I have an example. No, I do not have an example. That's not good. Let's try an example right now. So let's say we have you want to solve for the integral of 2x. No, wait, maybe I'll go for 3x squared multiplied by x cubed to the power of x cubed plus 1 to the power of 10. How would you solve this? One way you could do it is to go and do binomial expansion on this guy, and you get all 11 terms. And then after that, 3x squared multiplied by all this. Then you distribute into all 11 terms. And then you integrate term by term, correct? But would you want to do that?
No.
No. So that's why you have to use this formula. The key trick you need to realize is that in between the brackets is your fx. Then this is your n. Right, power 10. Square bracket. Okay, maybe I use square bracket to make it follow the format. Okay, then after that, this guy here in front is your f prime x multiplied by it. So using the formula, what you end up with is x cubed plus 1 bracket to the power of 10 plus 1, 11, divided by n plus 1, which is 11 plus c. That's it. Done. So simple. How do you check that you you integrated correctly? You differentiate your answer. Yeah. So let's see if we get back the same integrand, the thing you are trying to integrate. 1 over 11 you factor out. differentiate x cubed plus 1 to the power of 11. You bring down the whole power, then times x cubed plus 1, keep the same base, but minus 1 to get the new power. Don't forget to use chain rule. Differentiate x cubed, what do you get? 3x squared. Anything to cancel away? Yes, 11 cancels away. Then you are left with x cubed plus 1 to the power of 10 times 3x squared. Rearrange, I get 3x squared in front, multiplied by square bracket x cubed plus 1 to the power of 10. Is it the same format? I mean, is it the same integrand?
Mm-hmm.
Yes, all? That's the trick. Okay, but you must have f prime inside. What's between the square brackets? The derivative f prime must be multiplied in front of it. This is what we call the reverse chain rule. Reverse chain rule. Why? Here, when you differentiate, you have chain rule, which introduces a factor of 3x squared. So now we are trying to work backwards. We're trying to work backwards from this differentiation. Okay, because integration is the reverse process of differentiation. Okay.
Okay.
Yeah, okay, good. Then let's continue, try a few more examples. Let's try. What have we not covered? Actually, I can't remember what we covered already. I think question 4 we covered already, is it? Maybe not. We'll see, integration techniques. Oh no, no, I haven't. Yeah, I didn't go through all this. This one in class examples. Let's try one example, which is question 4 part 1. Question 4 part 1. Oh. No, not this worksheet. Okay, so question 4 part 1, I'm using this notation fx equal cosine x, gx equal sine x. So in the part 1, we want to integrate f of 2x. So it's just cosine of 2x. Agree? Then g of 3x will be sine of 3x, right? How do you integrate this? Whenever you have a product, you need to refer to your MF26 or your ultimate cheat sheet for the integration techniques. When you got product turned into sum, you need to use the formula over here. This is something new. So how do we use it? Let's see. Copy and paste. What you need to see is that the p plus q, the half p plus q and the half p minus q is really just referring to p plus q over 2. It's just written in a funnier way. Let me just write it down. P plus q over 2. That guy is p minus q over 2. Now the question, when you see cosine on the left multiplied by sine on the right, which form does it look like? 1, 2, 3, or 4? Focus on the right hand side.
I mean, it looks like the second one.
Correct, the second one, right? So we're gonna look carefully at this second formula. We have sine p minus sine q equals to 2 times, right? I'm just gonna bring the 2 over, so I get half square bracket around the whole thing. Then times the cosine of p plus q over 2 times the sine of p minus q over 2, like this, right? The key trick is, how do you get p? If I call this guy the L and I call this guy the R, left and right. How do you recover p? How do you get a formula for p in terms of L and R?
Oh.
Isn't it just L plus R?
Okay.
Correct. How about Q?
L minus R.
Very good. Okay, so now we know how to use the formula. This p plus q over 2 is really just acting as your 2x. This p minus q over 2 is acting as your 3x. So that means your p over here is really just, I'll just use the formula now. I get a half open square bracket sine of p, then minus away sine of q, close the square bracket dx. What's my p? L plus r. So it must be L is 2x, r is 3x. So this must be 2x plus 3x, which is 5x. And for the other guy, it must be L minus R, which is 2x minus 3x, which gives you negative x. Yeah,